Hello everyone, welcome back to my YouTube channel. My name is 𝗪𝗛𝗟𝗓 and I am currently working as an SD2 at Amazon. In this video, we are going to talk about the adapter design pattern. So far in this series, we have already covered the solid principles and we have also explored two very important creational design patterns, the factory method pattern and the abstract factory pattern. We will cover more creational patterns later in the series, but today we are starting with our first structural design pattern, which is the adapter pattern. Now, what is the key difference? Creational design patterns are used to create objects. On the other hand, structural design patterns focus on how different classes or objects are connected together, basically how they interact and fit with each other. Before we move forward, if you haven't liked and subscribed to the channel yet, make sure you do that. It really motivates me to create more such content. Alright, let's get started. Let's understand the adapter design pattern with a simple example. Imagine you are building an e-commerce website and you need to integrate payment gateways into your system. Now there can be multiple payment gateways, for example, Razorpay and Stripe, and it should be completely up to the user which payment gateway they want to use. Here comes the challenge. Each payment gateway has its own interface, meaning the inputs they expect might be different from what your application provides. For example, your application might send data in one format, while Razorpay or Stripe expects it in a completely different format. So how do we connect these incompatible interfaces? This is exactly where the adapter design pattern comes into the picture. Now let's dive deeper and see how we can implement this in code. So let's start with a simple implementation without using any design pattern. Imagine this. Your main class is your e-commerce website, and inside it, you have a payment processor. Now, whenever a user wants to make a payment, you simply call processor.payAmount payment type. For example, if the user selects Razorpay, you pass the amount in Indian rupees. If the user selects Stripe, you do the same. Sounds simple, right? But here's where things start getting interesting. Each payment gateway has different requirements. Let's take Razorpay first. Razorpay does not accept the amount in rupees. It expects the amount in paise. So if you pass 500 rupees, Razorpay will treat it as 500 paise, which is completely wrong. To fix this, we need to convert rupees into paise by multiplying the amount by 100 before making the payment. Now let's talk about Stripe. Stripe doesn't work with INR directly. It expects the amount in US dollars. So if you want to process 500 rupees, you need to convert it into dollars. Inside the payment processor, we've written logic like this. If the payment type is Razorpay, we convert to paise and call make payment. If the payment type is Stripe, we convert to dollars and call charge. So basically the processor is doing gateway selection, currency conversion, and method invocation, all in one place. At first glance, everything works fine. If we execute the code is working as expected. But we have some serious problems. The first issue is tight coupling. The payment processor is directly dependent on Razorpay and Stripe. The second issue is violation of the opens-closed principle. If tomorrow you want to add PayPal or any new gateway, you must modify this class again. The third issue is scalability. As more payment methods are added, this if-else block will keep growing and becoming harder to maintain. The fourth issue is single responsibility. The class has mixed responsibilities. It is handling conversion, decision-making, and execution all together. So yes, the code works, but it's not clean, not scalable, and definitely not future-proof. And this is exactly where design patterns come into play. Now, let's fix a design problem in our payment system. We need to separate responsibilities. Here's the idea. What if we move the payment gateway selection logic into a separate class called a payment factory? This factory will expose a method called getPaymentMethod. It takes a simple input like Razorpay or Stripe and returns the correct payment object. But here's the catch. We don't want to return random objects. We want to return a common type. So first, we define a contract. Our getPaymentMethod will return payment strategy. But we haven't defined payment strategy yet. So let's create it. We define an interface called payment strategy with a single method, pay. Now comes the interesting problem. Our actual classes like 𝗬𝗓𝗡 and stripe do not implement this interface. So we cannot return them directly from the factory. And this is exactly where the adapter design pattern comes in. Let's start with 𝗬𝗓𝗡. We create a class called 𝗬𝗓𝗡_adapter. This class implements payment strategy. Inside it, we create a 𝗬𝗓𝗡 object. Now when the pay method is called, we convert the amount from rupees to paisa and then call 𝗬𝗓𝗡's actual payment function. Similarly, we create another class, stripe_adapter. It also implements payment strategy. But this time, we convert INR to dollars and then call Stripe's charge method. So now, both adapters follow the same interface, which means they can be easily returned by the payment factory. Now let's connect everything together. If the user selects 𝗬𝗓𝗡, the factory returns 𝗬𝗓𝗡_adapter. If the user selects Stripe, the factory returns Stripe_adapter. Now we update the payment processor. We create an object of payment factory, call getPaymentMethod, and get back a payment strategy. And then we simply call paymentStrategy.pay. Now let's see what we achieved with this design. Conversion logic moved to adapters. Decision making moved to the factory. Payment processor now has one responsibility only. System is now easily extensible. In the future, if we want to add a new payment method, we just create a new adapter, update the factory, and we're done. No changes in the processor. And that is the power of combining adapter pattern plus factory pattern. Now let's quickly visualize the UML difference. First, the system without design patterns. We have our main e-commerce application calling the payment processor. Inside the processor, everything is tightly coupled. It decides the gateway, handles conversions, and even talks to external services. Basically, one class doing everything. It works, but it's not scalable. Now let's look at the improved design. Same entry point, but much cleaner architecture. The payment processor no longer decides anything. It delegates that responsibility to the payment factory. The factory simply decides which object to create. But external services like 𝗬𝗓𝗡 and Stripe have different interfaces, while our system expects payment strategy. So how do we bridge that gap? Using the adapter pattern. We introduce 𝗬𝗓𝗡 adapter, Stripe adapter. These adapters act as a bridge. They convert external interfaces into the format our system understands. So now the flow becomes factory returns payment strategy, which is actually an adapter. Adapter calls the real service. Payment processor just calls pay. No confusion, no coupling, no mess. And now we have clean separation of concerns, better scalability, flexible system design. And with that, our adapter design pattern implementation is complete. In the next video, we'll go even deeper into patterns like strategy pattern. Thanks for watching. If you found this helpful, don't forget to like and subscribe. See you in the next video.